In this video, we're going to learn how to integrate vector-valued functions. In order to do that, we're going to need all of the techniques from single variable calculus and carry them over into integrating vector-valued functions. So the integral of a vector function is equivalent to taking the integral of each component function. If r of t equals f of t, g of t, h of t, then the integral of r of t dt is going to be the integral of f of t dt, the integral of g of t dt, the integral of, scroll down a little bit, h of t dt, and then plus some constant vector. Okay. You can incorporate this constant vector into each of these indefinite integrals. So you can say plus c1, plus c2, plus c3, or you can define it just as some constant vector that has to be added to the vector we get after integrating each component function. The fundamental theorem of calculus applies for continuous vector functions as well. So now if we have a definite integral from a to b of r of t dt, then that's going to be equal to r of t, capital R, we'll use as the antiderivative of r, evaluated from a to b. So that's going to be r of b minus r of a. So we evaluate the vector function we get after integrating at t equals b and subtract the vector function evaluated at t equals a. So let's jump into some examples. Evaluate the following integrals, the first being the integral of t to the fifth plus t squared, e to the negative t, cosine squared t times sine t dt. So we can separate these out. Okay, so we can take the integral of the first component function, t to the fifth plus t squared dt, and we can integrate e to the negative t dt, and the integral of cosine squared t sine of t dt. Okay, so integrating that first component function would require the anti-power rule. So integral of t to the fifth is t to the sixth over 6. Integral of t squared is t cubed over 3. And then in this case, I'll write plus c1, so some constant for that first component function. Then we'll integrate e to the negative t. So I'm going to underline negative t. That's what you would make a u in a u substitution. What you'll see is I try to integrate these without separating the u substitution out. So the derivative of negative t is negative 1 over negative 1 to keep that equivalent. Circle the negative 1 as the derivative, or the du part, of a u substitution. So our integral then would be negative e to the negative t plus c2, some constant for this antiderivative. And then our last integral of cos squared t sine t dt. So if we were doing a u substitution, cosine t would be our u. Then the du would be negative sine of t dt. So negative sine of t gets circled. That's the derivative. But I need to put this over negative 1 to account for the fact that we added a negative into this integral. You could also put it outside if that makes more sense to you. And then we integrate. So really, we're thinking about this like a u squared integral without actually writing out the steps of a u substitution. So if we were integrating u squared, it would be u cubed over 3. So now, just without replacing it, we'll have cosine cubed t over negative 3 plus some constant for that antiderivative. So the antiderivative of that original vector function is t to the sixth over 6 plus t cubed over 3 plus c1, negative e to the negative t plus c2, and negative cosine cubed t over 3 plus c3. And again, we could write this as just t to the sixth over 6 plus t cubed over 3, comma, negative e to the negative t, comma, negative cos cubed t over 3, plus some c vector, which would be the constant vector that's made up of c1, c2, and c3. All right, evaluate now the integral of t times natural log of t, I, plus t cubed over 2t to the fourth minus 7j, plus cosine of 5tk dt. So they gave us the vector function now in terms of ijk as opposed to vector brackets. Again, we can separate out our integrals. So the integral of t times the natural log of t dt, the integral of t cubed over 2t to the fourth minus 7 dt, and the integral of cosine of 5t dt. Okay, so to evaluate our first integral, t natural log of t, that's going to require the integration by parts. So I like to do this in a table setup, u and a dv. So the acronym when we're going integration by parts that I like to use is LIPIT. Okay, so logarithmic, inverse trig, polynomial or polynomial-like, so square root of x, for instance, would fall under that category, exponential, and trigonometric. And you work your way across, whichever one comes first is the function that you put in the differentiation column, our u, and then the other part goes in our integration column, our dv. So here, a logarithmic function, natural log comes first, so natural log of t, and then t goes in the integration column. The derivative of natural log of t is 1 over t. Now, we sometimes proceed with more derivatives, but in this case, the derivative is not going to approach 0 or go to 0, so we stop. Now we pick up the integration column, so the integral of t is t squared over 2. And because the derivative is not going to go to 0, we have to set up another integral. So we go down and back across. So plus and then minus. So coming out of this column setup, we get t squared over 2 times the natural log of t minus the integral of the function we get by multiplying t squared over 2 by 1 over t. So that's going to be t over 2 dt. Now this integral we can handle without an integration by parts. So we have t squared over 2 natural log of t minus t squared over 4, the antiderivative of t over 2, plus c1, some constant for this first antiderivative. Now, second component, integral of t cubed over 2t to the fourth minus 7. So again, approaching this as a u substitution without actually breaking out into a separate u substitution, we would make u equal to the denominator, 2t to the fourth minus 7. So then du, the derivative, would be 8t cubed. So we have a t cubed term in the numerator, so we put an 8 there. And in this case, I'll put the 1/8 in front, just so we see a little bit of difference in how I did it on the previous slide. The derivative, the du, gets circled, so that's 8t cubed. And now we integrate, so that's going to be like integrating 1 over u, if we were actually writing out the steps of a u substitution. So the integral of 1 over u would be the natural log of the absolute value of u. So now we just do that without replacing 2t to the fourth minus 7, so it's 1/8 times the natural log of the absolute value of 2t to the fourth minus 7, and plus c2, constant for this integral. And then our last integral, the last component function, cosine of 5t, again requires this u substitution like integration technique. So underline 5t, that's what we would make u. Du then would be 5. And then I'll again put the 1/5 in front, so that keeps it balanced, right? We haven't changed the value of the integral, we just changed how it looked. Circle what would be your du, which in this case is 5. So now we're integrating cosine of u, which would just be sine, well, 1/5, sine of u, but u is 5t. So sine of 5t plus c3. So our vector function that we get from integrating here is t squared over 2 natural log of t minus t squared over 4 plus c1 1/8 natural log of the absolute value of 2t to the 4th minus 7 plus c2. And then 1/5, I need to give myself a little more room, so let's move that over. 1/5 sine of 5t plus c3. Right? In this case, I'll write out the alternative, or we can write that as t squared over 2 natural log of t minus t squared over 4, 1/8 natural log of the absolute value of 2 to the 4th minus 7, and then 1/5 sine of 5t plus a c vector, right? The constant vector whose components would be c1, c2, and c3. All right, next we have a definite integral now. So the integral from 1 to 2 of 1 over ti plus t times the square root of 3t squared plus 1j plus t plus 4 times the square root of tk. So again, let's separate out our component integrals. So integral of 1 over t dt from 1 to 2. Then we have our integral of t times the square root of 3t squared plus 1 dt, evaluated from 1 to 2, and then integral. So in this case, I'm going to distribute out the square root of t here before we do our integration. That's going to make it a little bit easier. So we'll have t to the 3/2 plus 4t to the 1/2 dt, 1 to 2. Right? That's going to just require the anti-power rule then if we complete that distribution. Okay, so now we integrate. So the integral of 1 over t is just the natural log of the absolute value of t, evaluated from 1 to 2. So we have natural log of 2 minus natural log of 1, which if we recall, natural log of 1 is 0. So just the natural log of 2 for our first integral. Now our second component integral, use that same technique. So we would make u equal to 3t squared plus 1. So du in a u substitution would be 6t. We have the t, we need a 6, so I'll put a 1/6 in front. You could also write over 6. Circle what would be your du term. And now we integrate u to the 1/2. Right? So u to the 1/2, but it's going to say 3t squared plus 1 instead of u, is going to be to the 3/2 power times 2/3. And we're going to evaluate that from 1 to 2. So let's see. The 6 and the 2, 1 and a 3. So we have 1 over 9. And if we plug 2 in, 4 times 3 is 12, plus 1 is 13. So 13 to the 3/2 is equivalent to 13 square root of 13, just a little bit nicer. And then minus 1/9. And if we plug in 1, so 1 squared is 1, times 3 is 3, plus 1 is 4. So 4 to the 3/2, well, we can actually take the square root of 4, which would be 2, and then 2 cubed would be 8. So we have 13 square root of 13 minus 8 all over 9, or 1/9 times 13 rad 13 minus 8 would be equivalent there. And then we have the integral from 1 to 2 of t to the 3/2 plus 4t to the 1/2 dt. So we'll get t to the 5/2 times 2/5 plus t to the 3/2, and then 4 times 2/3 would be 8 over 3, evaluated from 1 to 2. So we get, 2 to the 5/2, so that's going to be 2/5. So that's going to be 4 rad 2. And then plus 8 over 3, 2 rad 2. And then minus 2/5 minus 8/3. Okay, so if we combine our like terms, which I've done just to save us some time, is going to be 104 rad 2 over 15 minus 46 over 15. Right, you can check, find the common denominator of 15 for all of these four terms. Then we can combine the square root of two terms, and we can combine the constant terms. So that leaves us, and this one, we'll write ijk. We probably should have done ijk in the last slide. Right, the notation is interchangeable, but let's write that. So natural log of 2i plus 13 rad 13. Now let's fix that. That doesn't look that nice. 13 square root of 13 minus 8 over 9 j plus 104 square root of 2 over 15 minus 46 over 15 k. Right, we don't need any c vectors, any constant vector, because this was a definite integral. Right, and this is the integral we would get, or the vector we would get. All right, find r of t given r prime of t equals t squared 3t 5 and r of 1 is 1, 2, 3. So this is what we refer to as initial value problem. So they've given us the derivative of r of t as well as an initial value. At t equals 1, we know the vector will be 1, 2, 3. So we can use this initial value to solve for that constant vector we get in an indefinite integral. So integrating r prime of t dt is equal to the integral of t squared 3t 5 dt. So we are going to have the integral of t squared dt, integral of 3t dt, integral of 5 dt. In this case, not sure it's necessary to separate out into our component integrals, but feel free to do what makes sense to you. Integrating t squared is t cubed over 3 plus c1. 3t would be 3 over 2 t squared plus c2. And the integral of 5 would be 5t plus c3. Okay, so right now, r of t is equal to the vector function t cubed over 3 plus c1, 3 halves t squared plus c2, and 5t plus c3. And again, if you prefer, write it as t cubed over 3, 3 halves t squared, 5t, plus a c vector. It'll wind up getting us to the same point. So now, if we evaluate this vector function at 1, we're going to get 1/3 plus c1, 3 halves plus c2, and 5 plus c3. And they told us, based on the initial value problem, that this is equal to 1, 2, 3. So essentially, we get three equations where we can solve for c1, c2, and c3 accordingly. So 1/3 plus c1 equals 1. So that means c1 equals 2/3. 3 halves plus c2 equals 2. So c2 equals 1/2. And 5 plus c3 equals 3. So that means c3 equals -2. So now we can go back and write r of t without the c1, c2, and c3. So just remind myself, so t cubed over 3 plus 2/3. And then we have 3 halves t squared plus 1/2, and 5t minus 2. And here we can write these as one expression or two separate, doesn't matter. But this is an example of an initial value. So really in this video, it's all about our integration techniques. All of those single variable integration techniques. As you see, I like to handle u substitution within the problem. If it's more comfortable for you to actually go out and do the u substitution, I would encourage you to do that. Write your u equals, your du equals, and complete your u substitution, and then go back in terms of t. But if you can make sense of doing it more directly, it will pay off when we get to our double and triple integrals later on in this course.